So the moon now is a new place. It's a new place because of an armada of robots that have gone to the moon in basically the last 5 years. It started with the Japanese. A brilliant mission known as Kaguya, also called Selene, has been at the moon. It ended its mission last summer, but it produced beautiful HD TV quality fly-arounds of places on the moon. These are some of the biggest mountains on the moon. These are 4-kilometer high central peaks of the crater Tycho. The crater Tycho, we think, was formed about 95 million years ago when dinosaurs roamed the Earth. So this is a real mountaineering peak. John Grunsfeld, the astronaut who served to Hubble, he'd like to go climb the Mount Tycho, or whatever we call it. But this data was collected by the Japanese mission that started in ushering ourselves back to the moon. So why go back to the moon? Everything on the moon happened a long time ago. The reason is the moon is a history book. On Earth, we're interested in what happened since the dinosaurs, since we've roamed the planet. But on the moon, we're interested in other things. For example, before the mission known as LRO that NASA Goddard launched, this was the best topography of the moon. If you wanted to land there, your accuracy of that landing site was good to 1,000 feet. So imagine coming in to land in Washington, saying, well, we hope the airfield's within 1,000 feet. Wouldn't be the safest landing. Now we have new maps that not only look better from an instrument built here at NASA Goddard on the Lunar Reconnaissance Orbiter, but the quality vertically is good to about a foot. So we can now plan landings more safely. We can go to the interesting places and land. So one of the things we're doing now with NASA's return to the moon with robots is mapping the planet at the scale that you guys can choose to use if you want to go back to that planet. We didn't do that with Apollo. We went with elegant engineering and brute force to the safest places we can get to. Turns out the moon's also interesting for another reason, probably something you've seen on Jeopardy. There are places on the moon, you see their names floating around here, that actually are permanently shadowed from sunlight. That means they are the darkest, coldest places, inside some of these craters at the South Pole named for famous explorers, that we ever understood. In fact, inside those shadowed areas, it's colder than the planet Pluto, or I should say, the dwarf object formerly known as a planet, Pluto. So here's the moon. Inside those cold places, you could actually entrap frozen stuff like water, hence ice, and the ices that are trapped could record a couple of billion years of the collisions of the moon with comets. Now, do we care about comets? Yes, because some scientists believe that comets help seed our oceans with some of the chemical building blocks that led to life. So here's the telescopic view of the moon. We now see the moon in 3D at the scale where you could drive a car across it and plant landing strips. We've gone from the era of looking at the moon through telescopes to being there in person. Our Lunar Reconnaissance Orbiter is there now, about 45 kilometers above the surface, mapping the moon at scales where there's that crater Tycho, where you could plan a landing site on the peak of a mountain if you wanted to go there. One of the revolutions about the moon we learned from the Apollo missions that we can now show you in depth from these new maps is the fact that it has all these craters, these circular depressions, is actually important. Now, why should you care about craters? I happen to study them. I'm sorry, it's a boring thing, but my wife said someone has to do it, so I'm doing it. This here is the topographic expression of a 1 trillion megaton explosion that shocked the moon 4.2 billion years ago that formed what's called the South Pole Lake and Basin. The impact collision there was so intense, it probably excavated the lunar mantle through the crust, brought up stuff that we would never get to. We want to sample this basin. We didn't even know it existed until these measurements. We see these big cosmic collision scars on Mars, on the moon. We're looking for them on Venus, haven't found them. And they're actually great windows into the history of planets. So now we see them. We know where they are. We can figure out how to sample them. So all the data you see here was collected in the last year. The Lunar Reconnaissance Orbiter has collected data for the last year on the order of 78 terabytes of data. That's more data for any object in the history of solar system exploration in one mission in 1 year. It does pay to have your own ground receiving station, if you wanted to know that. So one of the things we're really interested in is if you were to go back to the moon with people, where would you go? This is what the sun would do in the sky, rotating around one of the sites right here on the rim of the Shackleton crater, where some engineers think we could set up stations for people to live and have sunlight basically all but 60 hours every year. And this shows the shadowed areas which have not seen sunlight in 2 billion years. So we look at these places and wonder. Now, the other thing we've done, which is kind of history in the making, is we've actually taken photographs of the places where we've been on the moon. And these photographs are basically about 3-foot resolution. You can see the blast spot These are where they actually walked on the moon. You can see the trails. Now remember, this all happened in 1969. So in the 41 years since all this happened, nothing's changed. This is a planet where things work slowly. You can see the stations, all the features. There's the weird crater. This is the traverse they made on Apollo 14, the longest walk made by people. The Apollo seismic network. Here's another one from Apollo 15, all the drive paths. You see the 2 wheels. We can now see what we've done to other planets. I mean, this is something you'd expect in the Smithsonian. We haven't brought back these pieces. Here's the Challenger descent stage. That's what brought us to the moon and then blasted us off. There's our flag, a little shadow. So now we found the collisions of the first Russian probes on the moon. We could, if you were there, we could probably see you waving, but we're not there, so couldn't do that. We've, of course, counted a lot of rocks. I won't bore you with those and move on, but I just want to point out that we've done a lot at the moon, and it's kind of a cool place. One of the other things we've observed on the moon, and I'll quickly cut to this as we go, is in fact, there are places on the moon that are so cold, they're off the charts. Some of these shadowed areas are 25 degrees Kelvin. That's cold, folks, colder than liquid nitrogen. We didn't know that. We've measured again the topography, and just a little summary of what we've already done with this mission known as LRO. Starting in September, the Lunar Reconnaissance Orbiter, built right here, some of you may be working on it this summer, will transition into a science mode. Now this is a view of the place, right in that shadow, where the L-cross collision occurred last October 9th. We smashed a leftover piece of a rocket and watched what happened when we collided with the moon. And guess what? It kicked up the kind of stuff that can be vaporized, like we think water, hydrogen, and even mercury, the kind of mercury in your thermometer. So these are views of the moon as if you were flying in a helicopter across the surface at about, in this case, about 50,000 feet. Pretty cool. This is the L-cross experiment. It was co-launched with LRO. It took its time getting around to the moon. This is the flight dynamics that is something that's pretty amazing that we can do. We threaded the needle of the rings of Saturn. We went to the moon with it, and in fact, you can see what we did to get there. So there's LRO went straight. This thing looped around for a while, actually for almost a year, and then collided with the moon. And the experiment was incredibly successful. Research papers are coming out in Science Magazine in the next month. So we're very excited about that. But L-cross was an example of women and men using ingenuity. They had something. We used LRO to target where to go, which we did, and then we collided the spent upper rocket stage with a small shepherding satellite with the moon, making a crater, exposing dirt, vaporizing, we think, ice, and measuring its signature. So you might say, well, were we allowed to do that? We were. As a planet that we do not think is a life-bearing planet, this kind of experiment is allowed. This kind of experiment would not be allowed on the planet Mars because we think Mars may or may, well, possibly had life. So anyway, the moon has come alive as a new world. We have another couple of years of mapping with the Lunar Reconnaissance Orbiter. We hope to send landers to the moon. This just shows an animation of what happened last October. And in fact, we actually impacted in a place in shadow, produced a plume that was received and measured by LRO on orbit with its far ultraviolet spectrometer. So pretty cool stuff. Mission was a total success, and I'm really proud of the team that did that. You can just see that again. Now, another thing we've done in our exploration of the solar system is visited near-Earth objects. And in 1999 through 2001, a little tiny satellite about as big as this, called NEAR, Shoemaker, visited one of the biggest near-Earth asteroids known as Eros. It mapped the surface of this rubble pile of silica-based rock, and then it docked with the surface. And one of the dreams we have for people going into space is, instead of leaping straight to Mars, actually going to visit near-Earth objects first. Why? Because they actually collide with Earth and are relevant to the history of life. 2, there are hundreds of thousands of them, of which 90% are uncatalogued. They're everywhere. There will be a close encounter with one in the year 2036. It'll come within the orbit of the Earth's moon to Earth, called Apophis. So we care. One of the theories now, one of the studies that we're doing in the agency is, what would it take to send you all to a near-Earth object where the surface gravitational acceleration is such that if you took a step, you'd escape? Be a great weight loss clinic, you know. You go from weighing 100 pounds or 150 pounds and you weigh 5 ounces on one of these small objects. It would be kind of neat.